those products. I'll hand it over to you now.
Perfect, Stefan. Thank you very much. So good morning, everyone. First of all, I think that I will start by introducing the team that today we will explain a little bit of what we do here as a research group in SREMat in KU Leuven. So first of all, you will see to my right, this is Michiel. Michiel, say hi. He's a doctoral student here in the group, and then he, together with Tobias, which is the next person, which is a postdoc in the SREMat group. They together they do a lot of research in the valorization of Bauxite residue. And I will hand in then to Toby.
Hello, also from my side. As Roberto said, I'm Tobias, a postdoctoral researcher here at KU Leuven, and I of course also want to introduce Roberto, who is a doctoral student here at KU Leuven in our group. And you will see also a bit his main research topic, because he will work on porous inorganic polymers. But now I think it's time to actually start with our workshop. So what we want to produce today, or want to show you today, are basically two different binder systems. We want to show you how to produce an inorganic polymer, but also how to produce a hybrid binder system. And we also want to show you two products, basically, which we want to produce from that. The first product, you can see already here, the mold will be a self-compacting slab, which we want to demonstrate you. And on the other side, we will show you then how to produce a porous material using an inorganic polymer recipe, basically. So the first thing will be the hybrid binders, which we want to present to you. And the hybrid binder is kind of a compromise technology between a normal cement and an inorganic polymer. The reason for that is we basically add a slight amount of cement together with the main precursor, which will be a slag, for instance, like coronel, boliden, or theoretically also vitrified red mud. And we have some filler materials. You can see that here on that bench, for instance. Here you see, for instance, limestone, which we can add here as a fine filler material. We can also add a coarser aggregate, which in this case is sand. And very important for these hybrid binders are additives which we can add. For instance, here in this case, you see in this yellow color, super plasticizer. And the advantage of these hybrid binder systems is that we can use additives that also work in cement systems. So that is the biggest advantage for these hybrid binders compared to inorganic polymers. And Michiel will now show you how to produce one of these hybrid binders. And what I want to mention also is that this work is based also on a patent that was filed from the KU Leuven, and the work was initiated by Lucas and by Yannis, basically. So Michiel will start now to add an alkaline activator. We still need an alkaline activator in these hybrid binders, but the molarity of these hybrid binder activators are much lower compared to an inorganic polymer system. So in this case, he adds 1 molarity sodium hydroxide. The next step is he adds a slight amount of cement. In this case, it is around 10 weight% of ordinary Portland cement. And as next, he adds, in this case, a ground granulated blast furnace slag. That's a different type of slag than the coronel, for instance. And we add that as a reactive slag to enhance the early age performance of this material. And the main precursor, you can see that also of the size of the bag, is in this case coronel slag. As mentioned before, we could also use here the boliden slag or vitrified red mud or bauxite residue. And these are basically the three binder components that we add to that mix with the alkaline solution. Now he adds calcium carbonate, so a limestone filler material. This is a very finely milled limestone, and we add this material also to enhance the particle packing of this mix, and also to have nucleation sites for the binder product. So we basically can have more hydrates formed on that high specific surface. Michiel will now show you how that paste looks like. After just mixing these binders, the limestone and the activator, you see it's a very, very stiff mix, basically. So you see he has problems to move that. And what Michiel will do now, he will add these two additives, what we have, which basically help us to increase the workability of that mix. And that are typical additives which are also used in cement and concrete mixes to improve the workability of the mix. So you see it's a rather small amount what he adds, in this case around 1%. Maybe you can hear it already, the mix is changing at that moment. It takes some time to homogenize it well in the mix. But I think you can clearly see now the difference of the paste. It is almost like liquid. Michiel, can you tilt it a bit more for the audience? So there is no comparison anymore compared to what we had without these two additives. So it's really flowing like water, basically. And that is what we want. We basically can, with this hybrid binders, use these additives and can limit the liquid, what we added at the beginning, as much as possible. And the last step, we still want to also add the aggregates. That was the sand in this case. Which is now slowly added to the binder mix. And after a certain time of mixing, normally we always go to a higher mixing speed to really have a homogeneous mortar or paste in this case. You've also seen Michiel scraped a bit the sides of the bowl, the mixing bowl, to really have all the materials what he weighed in, also in that mix. And now the next step is basically to just cast this this paste or this mortar mix in the mold, in that slab. And you can see how well it flows out of the mixing bowl. And we didn't use a lot of activator in this case, but as mentioned at the beginning for the mix design, the additives that are working for cementitious systems also work in these hybrid binders, because we can use an alkaline activator of lower molarity, and they are basically stable in this environment. So you can see how self-compacting this mix is. And important to mention is here again that the main ingredient is an iron-rich slag. And as also mentioned at the beginning, we cannot only use coronel slag or Boliden slag, we can also use vitrified bauxite residue. So that is actually vitrified bauxite residue that was produced for this project. You see now still it's relatively coarse. So the next step would be basically to mill this material to a fine specific surface area, similar as the other slags, and then it could be used as a precursor, for instance, for this hybrid binder mix. The next product what we want to present you now is the inorganic polymer. In contrast to the hybrid binder system, we now have as a main ingredient the coronel slag, the boliden slag, or the vitrified bauxite residue. And we add an alkaline activator to it. So there is no cement at all inside. When we use these inorganic polymers, we need to add normally an alkali silicate activator, which basically dissolves this slag and forms after a while an inorganic polymer. Roberto will present a specific type of an inorganic polymer and a so-called porous inorganic polymer. So we want to have a porous material with pores in the matrix, basically. So I hand over to Roberto for the presentation of these porous materials.
Thank you, Toby. So as Toby was explaining a little bit, what we will introduce right now is a little bit of a tutorial of how to make a porous inorganic polymer. There are several reasons why we want to introduce porosity in our materials. One of the main reasons is to do it lightweight. Then when you do a lightweight material, normally you gain certain things. For instance, the material becomes more thermal insulating, or also the sun absorption becomes very high if you do it properly. So we try to reach this type of niche applications in order to have a high valorization of the iron-rich slags, or in general, as Toby said, we can use different slags like boliden coronel that we will use in this example. And then also you could use theoretically vitrified bauxite residue. So now Tobias will help me to show you what is the process. I will first of all introduce the materials that we will be using. As in the case of the guys explained before, the main constituent of this material, this porous material, is this, the iron-rich slag. In this case, we will be using coronel. Then we have an alkaline activator, which is basically the liquid to form initial slurry. And then we will have several other components, as for instance, we have here a little bit of ground granulated blast furnace slag, GGBFS, and also quartz flour. So first of all, we will start to making the porous material with the alkaline activator. I will give it to Toby. Toby will put it in the mixer, and with that we will start forming the initial binder, an initial paste that we can actually use as a matrix to create this porous material. The second component is the iron-rich slag. In this case, it's coronel. I will hand it to Toby. He will start adding this iron-rich slag to the alkaline activator while he mixes. Yeah. So for instance here, what you can actually see is that we are using a different mixing type. In the case of the guys, they were using this type of mixer, which is quite good to homogenize materials which are dense, which are not porous. But in this case, we are also using an impeller that will allow us at a certain point of the process to introduce quite a lot of air in the mixture. And I will explain you later why we want to do that. Now Toby is adding the coronel into the mixture. He will add it right now all at once. Perfect. Then he will start creating an initial, that's the beginning act, the formation of the binder. The second component is actually the GGVFS, which is the second main constituent of the mix design. Toby will also add it all at once. While doing research in the years that we have developing this kind of materials, we actually use the GGVFS for certain reasons. The most important reason is that the GGVFS will allow us to have a control over the process. As you listened in the presentations before, and also as Toby was explaining, one of the main goals of this project is to upscale this type of materials. Right now, I am showing you, or we are showing you, how to make it in lab scale. But actually, one of the main things that we need to optimize for upscaling this type of products, it is to control how the process evolves. So the addition of the GTVFS at a certain point, as I will show you later, will help us to control a process which is called expansion. And we will go to that later. Then the third component is a quartz flour. This is basically the last raw material in powder that we will add from the main components. And this quartz flour will take a particular function in the post-processing of the material. Now, what we are doing is just to create an initial paste. And maybe, Toby, when it's already a little bit homogenized, we can also show it to the audience. So right now, Tobias is going to show you how this paste looks like. It's a little bit different to what you saw at the beginning with the other mixture, but this is what we want. We want actually a viscous mixture, still, which is very, very castable, which is important for the next step of the process. So now we have it. Now we have the initial precursor, which is going to be after curing the inorganic polymer. The next thing that we will do is to introduce this little powder over here. As in the case of the hybrid systems that the guys explained you before, we make small additions of this type of components. This is called a surfactant and has a specific reason to be in the mix design. Now, Tobias will add that to the mix design in order to create something. While you are mixing, I was telling you that we introduced quite a lot of air into the mixture. That surfactant will allow us to keep that air inside of the paste and to create small bubbles. An analogy that you can follow over there is that you take a little bit of water and a little bit of soap in your kitchen. You will mix them together, you will stir it or you will shake it, and then you will create an initial foam. This is the same principle that we follow over there. Basically, by adding this surfactant to the mixture, what we are doing is to give the capacity to this mixture to keep all the air that is inside within the mixture, and we want that. Normally, when we are doing these things in the lab scale and also upscaled samples, we will mix for several minutes. But now we will do it a little bit faster. And the next and last component that we will introduce is this one. It is also a powder. We added in very small quantities, and this is aluminum powder, metallic aluminum. I will hand it in to Toby. He will add it to the paste. He will mix for around another 30 seconds. And then I will explain you what is happening with that aluminum. So now Tobias is going to homogenize that aluminum within the mixture. He will change it to high speeds. We want to have this aluminum powder all over the mixture. In that way, we can actually create a very homogeneous porous structure later. What is the main reason to add this aluminum inside of the paste? Well, there are a couple of reasons, but the principal is that we would like to create a porous structure. As I was telling you in the step before, we already create a little bit of a foam inside of the paste because of the addition of the surfactant. And what we are doing right now, Tobias will stop it. What we are doing right now is that that aluminum in the alkali system will react, and then we will create hydrogen gas inside of that paste. Now Toby is casting this mixture in the mold that we have prepared. And as you can see, it's very flowable. So we designed it to be very flowable also for an industrial process, thinking always to upscale these samples. What you perhaps will see in some minutes or some seconds is that this mixture or this paste will start racing. And this is because we are creating these hydrogen bubbles inside of that base with the aluminum that we just add. Normally, as I was telling you, because we have modified this mix design in a certain way to have it very well controlled, that process of expansion will last a couple of minutes. It can last actually from a couple of minutes to 10, 15 minutes. But actually, we have a couple of samples that we can show you to do it a little bit faster. So I will take this one. After this material here expands, this thing here will expand, you will have a material like this. As you can see over there on the top, you have a kind of a curved surface. We call it here in the lab a muffin top. Now you cannot see actually the porous structure here, but normally what we do here is that we remove the sides, normally, the muffin top, and I have also a sample prepared for that, so you can actually see it. If you remove that muffin top or the sides of the sample, what you will see is something like this. As you can see over there, then you have a porous structure. And as I was telling at the beginning, there are several reasons why we want to have this porous structure in our materials. First of all, this is very light. You can take it with one hand. It has very special properties, as for instance, it has a very low thermal conductivity. It has a very high sun absorption. And as Yanis once mentioned it as well, we can modify even further this material in order to have it, in order to get certain properties. And I will show you an example. If we take that and then we put it, for instance, into hydrothermal conditions, we will end up with something like this. As you can see, it changes the color. It changes the color because of the processing of the material, but also because you are forming different things inside of this, of the pores of this material. Normally, what you will form inside of these materials is this. Inside of those pores, then you will create also different crystals, as you can see in those pictures. And these crystals normally will help us to have different properties. As you can see in this picture here, we have zeolite formation. In those pictures over there below, then we have also calcium silicate hydrate crystals that will provide a very high specific surface that you can use actually for different applications. For instance, catalysis or for removal of pollutants for water streams. So we actually, with this type of materials, we try to valorize these metallurgical residues into a material that you can also use for different applications. And that's the main goal. And with that, I think we are finished with the workshop. If you have any questions, the team here, we are ready to provide some answers.